Thank you very much for this amazing opportunity to be here and to speak. So, about the title, I thought I will have to give a talk. I will give a talk for general audience, right? And not for general audience, so for experts in the area. And this is why I chose this. So this talk will not, most likely will not say anything about hyperarithmetical categoricity. But well, I kept the title. It's not a bad title. Right. I'm really going to speak on my main interests, and one of my main interests is the study of effective procedures in infinitely generated abelian groups. What is effective? Well, let's see. Before I explain what's effective, here's a brief plan. I'm going to give some definitions and brief history. Then I will speak on computable abelian groups, then even more about computable abelian groups, and then if I have time, by the way, what time do I have to stop?
Say 30 minutes,
okay.
25.
Okay, so in case if I have time left, I will speak even more about computable abelian groups. This is my plan. All right, so the definitions and the brief history. It really goes back to 1911 or something like this, where Max then, he studied effective procedures in group theory. And this actually predates the formal definition of an algorithm. It's very interesting by itself. Again, effective, I do not specify. The systematic study of effective procedures in group theory was initiated by Higman, Rabin, and Maltsev, where they already had the formal definition of an algorithm. All right? And I will mention that such studies can be generalized to other structures. I'm not going to speak about these things, but there are things like effective procedure in field theory and stuff like this. So people do this. Okay, here is the main definition in this talk, right? Due to Rabin and Maltsev, a countably infinite group has a computable presentation if its domain, its elements, can be identified with the natural numbers, so that the group operation becomes a computable function, a Turing computable function. Right? So you have a way to compute. You have an enumeration, one-to-one enumeration of all elements, first one, second one, third one, and you have a procedure which you say what's A1 plus A3, and it says okay, it's A10. It returns you a number of the sum. All right, so these are main objects. Of course, you may say, well, this procedure may be very, very inefficient. However, most of the groups in my talk will be polynomial time. I will say a little bit more about it. But in general, the original definition didn't say anything about the efficiency. Just computable, that's it. And if you know what's a Higman's recursive group, it's not the same, because Higman's recursive groups, they may have the word problem undecidable. Here, the word problem is decidable because you have this one-to-one enumeration of all elements, basically. So it's a more general notion. Right. Okay. So some simple examples. So for instance, the group of the rationals under the usual addition has a computable presentation. Okay. The second example is a little bit more complicated, still very trivial. So you take a set of prime numbers having a computable enumeration, so you can list, you say 2 is in, 3 is in, 11 is in, 13 is in. You are not sure if 7 is in unless you see it, so it may not be even decidable. But if you take the additive group of the localization of the ring of the integers by this set of prime, it has a computable presentation. It's not very hard to show, but well, I mean, just believe me. And actually, even more, this additive group has a computable presentation if and only if this set P is a computably enumerable set of primes. So if and only if, the first result, very easy. However, there are non-computable, computably enumerable sets, such as, say, the Holton problem. Right? Oh, well, okay, interesting. So in the characterization of computable, actually polynomial time computable group, you get an undecidable set, probably. Okay, so the next theorem is also quite interesting, and Massey showed that there exist two computable presentations of the additive group of the vector space of infinite dimension, countably infinite, which are not computably isomorphic. So yes, of course they are isomorphic, but you can't make the isomorphism computable, which is very interesting. Well, so if you restrict yourself to only computable things, your category becomes more complicated. So things which were isomorphic now are not computably isomorphic, they are different. And Maltsev and independently Rabin, they gave the following definition. They say that a group is autostable or computably categorical if there exists a computable isomorphism between any two computable presentations of the group. So for instance, this group is not computably categorical, right? But there are many of them. And the fundamental problems of abelian group of computable abelian group theory, not quite right. So computable abelian group theory are: the first, to describe the ones which are computable, which have computable presentations, of course, and the second, describe the ones which are computably categorical. And here, relative to a given oracle, I will say probably a little bit more about this, but for now, just ignore it. Computable, that's enough. Okay, and the first results, the first steps in the area, the simplest ones which you can think of, probably as just subgroups of the rationals under addition. And classically, they're very well understood, which is not very surprising. And Maltsev, he showed that the classical theorem can be sort of effectivized, right? So they have this notion of type, which is basically a set, more or less, up to finite difference, which is an invariant of your group. And he showed that this group is computable if and only if this type is computably enumerable. And this is an effective version of the well-known characterization, which is due to Baer in 1930s. So effective. You see effective, but involving probably even an undecidable set. So the next more recent result is the following theorem proven independently by 4 authors. Isamiev in USSR and these 3 people outside. Right. A certain characterization of computably, they obtained a certain characterization. It's too complicated to state in this slide because there is no way I can define it in all details, but they classified all computably presentable reduced abelian P groups of small Ulm length. Not too complicated P groups. Well, you can put your hands on them because they are not too far from just the direct sum of cyclic ones. Okay, and they used limit-wise monotonic approximations on functions. And important is that there exist non-computable functions which have computable limit-wise monotonic approximations. I don't want to define what are computable monotonic approximations, but the important here is that there are many functions which are limit-wise monotonic, but not computable. And this is another effective version of the classical result of Ulm, which basically describes the groups are up to isomorphism, the reduced abelian P groups up to isomorphism. Again, effective, involving some potentially undecidable function. Okay. So this notion was new even for pure computability theory. So typically, computable abelian group theory, it mixes some known results from algebra, some known methods from computability theory, and maybe some new ideas. But before that, I don't think there were any real applications of new ideas from within this sub-area into some other things, right? So there are some applications in computable combinatorics, in computable model theory, in computable combinatorics again, and even in degree theory, which is pure computability theory. So they show up in some very far area, still within computability theory, but very far. And an interesting question in this area, so I told you that was a characterization for small Ulam type, basically finite. It's still unknown if you can do the same for arbitrary Ulam type. So it's a big open question in the area, which is very surprising. You think you just take the classical theorem and put things which are, put some computable things into it and just run through the proof. It's not true, so you have to do something. Okay. More about computable abelian groups. So I didn't say explicitly what was effective, this question I started with. But here effective doesn't mean that you have something which is computable everywhere. So you speak about computable objects, even polynomial time objects, and you naturally get some algebraic invariants which are not even decidable. They may be even far from decidable. So for example, this problem of Kisamiev, this very simple group basically direct sum of very simple subgroups of the rationals which encodes a certain set of prime. So each piece encodes a prime number, so that the whole group encodes a set, right? And he asked, it's a very simple group. There should be an answer to this question. So he didn't know how to describe computably presentable groups of this form, for which sets P, this group is computably presentable. Such an easy group, it's just very annoying question, right? And he tried it himself, and he showed that this group has a computable representation with certain additional restriction, so that you can decide in which elementary summand you are, right? If and only if P is in a certain proper subclass of some hyper-immun sets, which is taken from recursion theory. So very strange actually, and it's not so. This hyper-immun sets, they're classical. They can be found in more or less every textbook on computability theory, but it's a proper subclass. So he showed it's a proper subclass. It's very strange. All right, and we were able to show that the 7 co-authors. Right? So the group, this group is computable if and only if P is computably enumerable relative to the second iteration of the halting problem. So you get the halting problem, then you take the machines with the oracle for the halting problem, and you look at the halting problem for these machines. And this guy is computably enumerable with this machine with this very powerful oracle, basically iteration. So the invariant is not even the halting problem, it's even there. So it's a halting problem of the whole and computably enumerable in it. And the group is safely assumed to be computable in polynomial time. So that this is true for if and only if polynomial time. Right? Actually, this relatively recent result, so this group is torsion-free. Every non-zero element has infinite order. Every torsion-free abelian group, which is computable, has a polynomial time computable representation. It's a result by Rod Downey, Sanzer, and who was it? Student of Sanzer. Udens, okay. So it's a recent result. So most of these groups are torsion-free, so you just automatically get the results for polynomial time. Okay. Some thoughts, in case I have time. So there is a very little hope to obtain a description of computably presentable abelian groups in general, and there are some results which say very unlikely. It's as hard as it could be by Downey and Maltelban. Also quite recent result. as for computable torsion-free abelian groups, they don't even have nice invariants in the classical sense. Forget about computability, just take the pure algebra. They don't have any invariance, unlike the, say, the reduced P groups. No invariance at all. And okay, you say, maybe for some special cases, it's more or less okay. But remember, this very simple group, which is torsion-free, it was an open problem for 25, 30 years. And the proof is not trivial at all, it's tricky. So there is something going on here, certainly. Okay, what about the complexity of isomorphisms? Let's see. So you remember that there is a group which is computable, however, it has a presentation which is not computably isomorphic to it, also computable, no computable isomorphism. So, good news, there is a characterization of, there are characterizations of computably categorical abelian P groups and torsion-free groups. However, it's not known if there is any nice description of computably categorical abelian groups in general, but these classes are very large classes, so it's more or less satisfied. However, there are examples of abelian groups which are not even computably categorical relative to the halting problem. So you allow your isomorphism to be computable in the halting problem, and still you get a group, very simple by the way. So you take the additive, the infinitely many copies of the rationals, and also add to the infinitely many copies of the Z. And this very simple group is already not computably categorical relative to the halting problem. Well, that's very surprising. Okay, so if things are hard, why don't we restrict ourselves to very simple groups? Just take a subgroup of the rationals, and take infinitely many copies of it, and just put them together, and ask the usual questions when they are computable, and when they are computably categorical, maybe relative to some oracle. Well, you know. And every group of this form is computably categorical in the second iteration of the halting problem, which is not bad. All right. And the proof is not easy at all. It requires some new algebraic technique. So you don't expect it in pure algebra, because these groups are so well understood. It's so trivial, right? Here, because you have to build your isomorphism step by step, you need some new algebra. Algebraists never do this step by step. And here you have to do it step by step using certain oracle, asking questions. New algebra here. All right. And it's well known that this group is not computably categorical. It never happens. Easy to see if you know some results. All right. So you have not computably categorical, but computably categorical into the second iteration. Well, this usual motivation from algebra, basically, not from computer science or computability. When is it computably categorical in the halting problem, in between? When exactly does it happen? And it's a natural question to ask. And here it's a certain surprise. We can characterize when exactly this happens using semi-low sets. What are semi-low sets? Well, I don't want you to read this. So semi-low sets, they were introduced by Robert Sohr in 1982 in the study of, so it's a pure computability theory. So, and he used this to show that the certain principal filter of supersets is isomorphic to the whole thing if the complement of this set is similar. So it's very far from computable abelian group theory, as far as you can imagine, within, of course, the computability theory. Yet it appears in the characterization. and there's some details. So, of course, all right. Well, I think I still have some time to say several words about the hyperarithmetical case. Well, I'm not going to define the hyperarithmetical hierarchy and stuff. I'm just saying that you can iterate this process, you know, halting problem over the halting problem, again over the halting problem, even up to, so proceed after omega, after the first ordinal, right? Limit ordinal, omega plus 1, omega, and this way you get this hyperarithmetical hierarchy. So it's very far. And here is the problem with Cherov. Very natural question, motivated by many results in computable model theory, but not in commutative algebra, I would say. Well, you have this hierarchy, right? Infinite. Does it collapse at all? Maybe every group is computably categorical somewhere very far, omega plus 2, maybe omega squared plus 2, something like this. And even more, is it true that every level of this hierarchy is proper, means that, you know, it doesn't collapse locally? So, for example, for well-ordered sets, it collapses only every second level is realized. If you're on the third level, you have to go down one step. So there are examples where it's not true. And the natural question was, okay, is it true for torsion-free abelian groups? And here is the strong conjecture. The proof is very hard to write down. This is why I don't want to state it as a result. Who knows, maybe it has some tiny mistake. But I'm almost 100% sure the proof works. And a very strong conjecture is that the answer to this problem is yes. And the proof combines everything I know about these groups, basically everything. Every single paper you may find on this subject. This method you will find there will be in the proof, which is very strange because most of the natural classes, it's not that hard. But this is an exception. And the question is, can you prove it simpler? I don't know. Thanks.
Any questions, comments?
So what is your alpha?
Alpha is the computable ordinal, which is an ordinal which has a nice notation, which is computable. Well, I told you I wasn't going even to get to the last slide, but I managed to do it. Right? So it can be found in the standard texts. We can talk about it later. Right.
Thank you.